All right. Get this going. Safety first, of course. So in this small section, we're looking at what's called thermodynamic and kinetic control. So when we think of this, we can have a potential outcome from one set of starting materials that produces different products. This happens a lot more in organic chemistry than it does in inorganic chemistry. However, it does still occur. So there's two reasons. The idea of relative stability of the products, which we call thermodynamic factors, and then the rate of product formation, kinetic factors. So if we're looking at this simple diagram, with the same starting material, there's the idea we can produce a blue colored product and a green colored product. They both have different activation energies. They are different transition states and different products. One of the things that's maybe not well illustrated on here is that if we were talking about these occurring at different times, there would be maybe a different state of where these would be found on the reaction coordinate. But not every model can be perfect. So, as I've already stated, similar material or same starting materials, different products, and these would be competing pathways because both of these would be occurring at the same time. Likewise, if you had enough activation energy to make the blue compound, you would easily have enough energy to make the green compound. Now, reaction 1 will be the faster reaction because it has the lower energy. It's more stable than the transition state, therefore a lower activation barrier. Again, you would assume these starting materials would have the same temperature. Therefore, product 1 is called the kinetic product. It forms the fastest. Reaction 2 is going to be lower energy than 1. Therefore, P2 is the thermodynamic product, more stable because it has lower energy, a bigger decrease in energy. So what this means is that at low temperature, where the available activation energy is low, it's under kinetic control. And the major product is from the fastest reaction. At very high temperatures, the reaction is under thermodynamic control, equilibrium, reversible conditions, and the major product is the more stable system. Because we often talked about in the previous unit that things that are thermodynamically favorable are going to have a higher likelihood than the kinetic ones. So this plays a big role in chemistry because you might want product 1, the green one, which means you want to have these things occur at low temperatures. Likewise, you might want P2, the higher one, with the higher activation energy, so you're going to want that at higher temperatures in order to be more likely to get that to occur. So, looking at this a little differently, whether the reaction is spontaneous or not, the kinetic barrier is the activation energy. So, the idea is that the activation energy is going to be pretty much connected to how fast it will go. The activation energy is the energy required to get to the transition state, right, at the top of the energy hump, that turns to the product. The reactions usually will need some energy input as activation to form the unstable intermediate. Smaller reactivation energy, more kinetically favorable. So if we have a reversible reaction, we can easily see that this smaller activation energy from A to B is going to be better than B to A. So in this case, we have smaller activation energy. The reaction progress is going to just be in this concept of A to B from a graphical standpoint. So this is looking like more B is going to be formed than A is going to be formed just based upon these little graphs. All right, so this kind of graph looks a little funny because it's probably not one you've seen before, to where C is our starting material, and instead of it going overlapping, they've just kind of shown this to separate. So if we had C become A or C become B, the idea is that these mixed products are based upon different energy components. So on the left side, we can clearly see the activation energy for this multi-stage is going to be less than it to make it for B, to get it to its transition state. However, we have a decrease in delta G that would be occurring. So the idea here is that this is going to be less energetically favorable, but because it has lower activation energy, it's going to have the kinetic product under kinetic control. B, though, with its higher activation energy, but you can see overall less energy, I have a feeling these delta G's should be delta H's, just to give you a heads up, because you usually don't have delta G on a graph like this. But the idea is that as we have B at a lower energy, it's thermodynamic or energetically favorable. So if that's more energetically favorable, it's likely to occur at a higher temperature than this would be, because it's at a lower temperature, to where lower temperature, this would be happening a lot. This couldn't happen as often. So you're going to have this occur when temperature is lower, this occur when temperature is higher. All right, coming with any kind of questions? Talk to you later. Take care.